Okay, now, we've seen that 8% quarterly for T years means that 2% is added 4 times every year, so it's added 4 T times, so that your principal, if I write this as a more general function using P0 instead of $1,000, okay, whatever, this will fit any investment, whatever you want, just plug in that number for P0. If you invest $8,792, then P0 will be $8,792. Okay, in any case, your P of T is going to be P0 times 1.02 raised to the power equal to the number of times you're going to add 2%, which will be 4T times for reasons that you should be thoroughly familiar with, if not by now, by the time you stop and really think this through. Well, I'll just comment, 1.02 to the 4T is 1.02 to the 4th to the T power. That's by the laws of exponents that you have to know. So if you don't know them, go to the laws of exponents right now, write them down, and look at them every day. Try to remember them and write them down every day until you can do it in your sleep. Okay, 1.02 to the 4th is 1.08243216. Okay? And I know that that's accurate because I know how many decimal places. I mean, I'm pretty sure that's accurate. That's what came off of somebody's calculator. But every time we raise this to a power, add 2 more decimals, we're going to get 2, 4, 6, 8 decimals. And the last decimal is going to be 2 to the 4th. The last 2 decimals will make up the 16, which is 2 to the 4th. So that works. Now, you don't understand a word I just said, but this is 1.02 to the 4th, and you understand that. And punch it into your calculator if you don't believe me. And tell me if I'm wrong, because I must have written something down wrong. But I'm pretty sure that's it, because I know how to expand this. Okay. So P of T is this raised to the T power. And I wrote something down that's plain old false. It's equal to P naught times 1.08 to that power. So we read that. I'll rewrite it here. P of T equals P sub 0, P naught times 1.08243216 raised to the T. And I wrote that pretty small. And people sitting in the back of the room aren't going to be able to read that, but there's nobody in the back of the room right now. That was an hour ago. And with your resolution, I think you can read that. If not, you see it here. Okay, so if we compound, now we could compound 8% daily. Now, when we compound daily, little technicality, we round off 365 1/4 days, which isn't even exact. We round off to 360. Okay, so we compound it 360 times a year because it's a lot easier to deal with 360 than 360.25, blah, 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 lots of decimals. Okay? Okay, well, then what's going to happen? If we compound 8% 360 times a year, well, we're not going to give you 8% 360 times during the year. 8% is your annual rate. We're going to divide that into 360 parts. Well, 8 over 360, that's like 1 over 45, okay, which is 0.02. I could figure that out, but I'm not going to. I know what 1/9 is, so I could go from there, but we're not going to do that. Okay, 360 times a year. We're going to add 0.08 over 360 of our principal to our principal. So, the 1 really represents P naught, and the 0.08 over 360 represents what we get if we add this much. Okay? And of course, we're going to do that 360 times every year. So just like we got 4T up here, we're going to get 360T up here, aren't we? Okay? So our function would be, for compounding daily, would be this. Okay? Now you can raise this to the 360th power if you want and compare it to this. Okay? It's going to be a little bit more. You get a little advantage. Not a big one, not as big as you might think. Okay? So you could calculate that. It would be, well, to calculate 1 plus 0.08 over 360 raised to 3/60th equals 1.082 what? It's going to be a little more than this. Yeah, so just to motivate you to look at these videos, I'm giving you extra work to do. Well, you don't have to do it, but it just takes a second and it's worth doing. Okay, now, we're going to abstract this. We might have any interest rate. Interest rates might even fluctuate, which gets kind of complicated. And we might compound it any number of times during the year. We might want to compound it every second. Well, it's going to be something like 330 million times a year, but we could do that. We could calculate it. Your calculator would do that just fine. Okay, so if we wanted to do that at some other rate, like 4% or 6%, or if you're lucky, more than 8%. But 8% is getting a little risky, so you probably don't want to risk that. Okay, so whatever the rate is, we want a formula, and whatever number of compoundings a year, we want the formula to address both of those, so that we have a formula for any starting principal, any interest rate, and any number of compoundings. Well, clearly our interest rate is here, our number of compoundings is here, and if we have the number of compoundings here, well, we're going to do that, whatever number of compoundings per year times the number of years, right? So that's going to go here too. So n, the number of times we compound it, could be 4, which we'd have if we did this one, could be 360, which is what we have here, but in general it's going to be n. And it's going to appear here because you're going to multiply how many times you compound a year by the number of years, aren't you? T being the number of years. R is the rate, so we're going to divide the rate by n, just like we divided the rate here. The rate was 0.08. We divide that by the number of times we compound it, so we split up the interest rate accordingly. So we get this. P0 times 1 plus R over n raised to the nt. Okay? So we want to understand this, and we want to completely understand how this is what you get if you get compound interest. Okay, now I'm going to pull a little magic on you, not that much. I'm going to say, well, what if we keep compounding, not every second, but how about every microsecond, or every nanopicosecond? Well, your calculator probably won't handle nanopicoseconds, but we know what it's going to be, because it's going to be so close to what we get if n, as n approaches infinity, because we're approaching, if we do it in a nanopicosecond, we're going to do this. The number of times we do this in a year is going to be like a number that before you get to the decimal point has, I think, 28 numbers before the decimal point. It's going to be a huge number of times per year. Okay? So we're going to let n approach infinity, and we can do that. Okay? Now we don't know exactly what we get when we let n approach infinity, but we know how to calculate it as accurately as we need it. So our limit as n goes to infinity of 1 plus r over n to the nt, we're going to say is e to the rt. Now we've already seen the exponential e to the x function. So e to the rt, remember e was a number that's pretty close to 2.7. It's approximately 2.71828. And then after that there's another 1828, but it doesn't keep repeating the 1828. That's just a 1 in 1,000 coincidence. Numbers like pi, it goes on forever. We can calculate it as accurately as we like. You can calculate it quite accurately with your calculator, but your calculator has a button on it that'll give you e to as many digits as your calculator will handle. Okay, you have an e to the x button. Just do e to the 1 power and you get e. So what's e? Well, in order for this to be the limit of this, e has to be the limit as n approaches infinity of 1 plus 1 over n raised to the nth power. Now, you can calculate that. You can put in 1,000,000. You can do 1 plus 1 over 1,000,000, raise it to the millionth power. You can punch that into your calculator. You get a number like 2.71828. It won't be quite accurate. Okay? So if you don't want n to be 1,000,000, let it be 10,000,000. Well, your calculator only goes so far, but you can calculate this pretty accurately on your calculator. And they're mathematical techniques. You've got to know calculus before you really understand those techniques very well. So we're not going to talk about the techniques we use to do E. We don't even really talk about that usually in a calculus course, although we could. Okay, so anyhow, E is this magical number, maybe the most important number in mathematics. You might think pi is, but pi is just based on E. Okay? You know, just based on E to a complex number, actually an imaginary number. I won't get into that. But that's one of the coolest things in mathematics, the way E and pi are related. And you can understand it at the end of a good calculus course. Can't understand it now, so that's all I'm going to say. Okay, well, this function, if you let n increase your number of compoundings, you get a continuous growth rate. And that would be e to the rt, where r is your interest rate. Okay, well, that's all we'll say about that for now, but we'll say a lot more about it next time.